Hello future engineers, welcome to my YouTube channel. If you're still new to my channel and you like what I'm doing, please don't forget to share my videos to your friends and to your friends' friends. That's one way you can keep me going, inspired and refreshed. Now if you find my videos interesting and important to your studies, also please don't forget to subscribe. So here is the problem on moment of a force about a point. A 600-pound force is applied to the wheel as shown. Determine the moment of this force about the center C, corner A on the curve. So one way is to resolve this force into its horizontal and vertical components. Then we compute the moment of the components about C. So since the total angle here with the radial line is 45 degrees, and the angle that this radial line makes with the horizontal is 30 degrees. So this is 30 degrees. Therefore, this angle that the 600-pound force makes with horizontal is 45 minus 30, so 15 degrees as shown. The horizontal component is 600 cosine of 15 degrees, and the vertical component, which is downward, is 600 sine of 15 degrees. So since the radius is 15 inches, the horizontal distance of the vertical component is 15 cosine 30. So from corner A also for part B, this radius is 15, and this is 15 minus 3, so 12, 12 inches. So by Pythagoras theorem, this horizontal distance is square root of 15 square minus 12 square, so that's 9 inches. So that's 15 cosine 30 degrees. Radius, hypotenuse, cosine of 15. This distance is 15 sine of 30, and that's 7.5 inches. Therefore, this distance is 12 minus 7.5, so 4.5 inches. So moment about C can now be computed. Let's consider counterclockwise positive. So 600 sine of 15 degrees times 15 cosine of 30 degrees. Then plus, because this is counterclockwise, 600 cosine 15 times 7.5. So moment about C can now be computed. 6364 pound-inch. Then the direct way is we compute the component of the 600-pound force into into radial rather component, which passes through C, so it is 0. The other component is the tangential component, which is 600 sine of 45, because this is 45. And the moment arm is 15 inches. So the direct way of computing the moment of the 600-pound force about center C is 600, the tangential component is 600 sine 45 times 15 inches. This is the tangential component, tangent to this point, and perpendicular to the radial line, which is 15 inches. So again, 600 sine of 45 times 15 inches. That's the direct way. You will get 6364 pound-inch and counterclockwise direction. Then for corner B, moment A is 600 sine 15 counterclockwise positive times 15 cosine 30 plus 9. Then because the moment of the horizontal component is clockwise, so minus 600 cosine of 15 times 4.5, the moment arm. So moment about A is equal to 806.9 pound-inch counterclockwise. Now for your part, use two methods to evaluate the moment of the 160-pound force about end C of the bent rod ABC when letter A theta is 30 degrees and B theta is negative 30. So this is theta, 30 degrees. When theta is negative 30, so it's pointing up to the right, and this is negative 30. So show that moment at C is equal to 1,600 pound-inch counterclockwise. Then for part B, 4371 pound-inch clockwise. So that's it for your part. Problem 69. For the system shown below, determine the angle theta such that the 5 kilonewton force applied at point A exerts the maximum moment about point C. What is the corresponding moment? So that the 5 kilonewton force will exert maximum moment about C, then this 5 kilonewton force must be perpendicular to the line joining A and C as shown. So if they are perpendicular, so this is 750 mm, square root of 600 mm square plus 450 mm square is 750 mm. So for maximum moment at C, due to this 5 kilonewton load, the force and this distance must be perpendicular, or else if it is inclined, then they are not perpendicular, then the 5 kilonewton force will not produce maximum moment about C. So if this is theta, this angle is 90 degrees minus theta, and because this is 90 degrees, so this is also theta. So from the figure, tangent theta is 600 over 450. So tangent of theta, 600 over 450, so theta is equal to 53.13 degrees. And the moment is clockwise. For the other angle, the 5 kilonewton load must be directed opposite to this direction, so up to the right and still perpendicular to 750, but theta is in clockwise direction and it is negative. So this should be theta for the second part, for the second possible answer. So theta here is the negative of 180 minus theta in part A. So theta is negative quantity 180 degrees minus 53.13 degrees. So theta is negative 126.87 degrees. So for part A, the moment is 5 times 0.75 clockwise. So MC max is 5 times 0.75, and MC max for theta equals 53.13 degrees is 3.75 kilonewton meter clockwise. Then when theta is negative 126.87, the maximum moment is still 3.75 kilonewton meter, but it is counterclockwise about C. So that's it for this part. And for your part, here's your problem for the system shown below. Determine the angle theta for which the 160-pound force exerts the maximum moment about point C. What is the corresponding moment? So these are the answers for part A. And for part B, for the other possible theta, that's the answer. So that's it for your part. Then moment of a force about a point, when the force is a force in space. So determine the moment of the 2 kilonewton force about A, corner A, and then B, corner B. So here's the given figure. That's the 2 kilonewton force. We mark this as C and D as our guide. So first, by the scalar approach, I will resolve the 2 kilonewton force into its rectangular components. So it is, let's select this as X, the Y, and the Z axis for moment at B later. At A, same is true, X, Y, and Z. So F is magnitude over distance. It is directed rightward, 0.3 along Y, then negative 0.2 meter along X. So that's why it is magnitude over distance along X, 0.2 square, along Y, 0.3 square, then negative 0.2 I because it is directed rightward and backward. Backward is negative, so negative 0.2 I. rightward is positive 0.3 J. So F is in rectangular vector representation, negative 1.1094 I plus 1.6641 J kilonewtons. So let's show it on the figure. So this is the X component, negative, so it's backward, and the Y component is positive, rightward. So MAX, therefore this is the X-axis. So the one that is parallel has no moment. The other one, 1.6641, passes through AX, so MAX is 0 by scalar approach. MAY, this is the Y-axis, so the 1.1094 passes through the AY axis, so 0. The other one is parallel, so no moment, therefore it is also 0. Then MAZ, this one, 1.1094 passes through the AZ axis, so 0. This one is negative because if you apply right thumb rule, the positive moment about AZ is in that direction. If you use right thumb rule in that direction. So this is opposite. So negative 1.6641 times moment arm, which is this 0.2. So MAZ is negative 1.6641 times 0.2. So moment about A is equal to AZ, negative 0.3328 kilonewton meter. So in vector form, moment A is negative 0.3328 K kilonewton meter. So that's the moment about A. By cross product approach, then moment about A is R AC cross the force. It may also be R AD cross the force. So I'll select R AC cross F. So AC is negative 0.3 along Y only. So 0 along X, negative 0.3 meter along Y, then 0 along Z. That's the position vector AC. Then components of the force, X, Y, then Z component. Unit vectors, copy the elements of the first two columns, then expand. So notice that it is just about Z. So 0 along I, 0 along J, but along K is 0 minus, this is positive, so negative minus 1 minus quantity negative 1.1094 times negative 0.3, and that is equal to negative 0.3328 K kilonewton meter. So negative of negative 1.1094 times negative 0.3 K. So MA is equal to negative 0.3328 K kilonewton meter, or simply its magnitude is 0.3328 kilonewton meter. Then about B, MA also is RAD cross F. So if we choose AD, it is the position vector is negative 0.2 I only. Then along Y and along Z, 0, 0. Components of force, unit vectors, then copy the first two column elements, expand 0 along I, 0 along J, then along K, negative 0.2 times 1.6641 minus 0. So negative 0.2 times 1.6641 is also negative 0.3328 K, or negative 0.3328 K kilonewton meter. Then about B, by the scalar approach first, using right thumb rule, this is the positive moment about BX direction as our guide, about Y, that's direction, and about Z in that direction. So moment about AX, so this is parallel, no moment. This has moment 1.6641, but it is opposite to this positive direction by right thumb rule. So MBX is negative 1.6641 times 0.1. And it is equal to negative 0.1664 kilonewton meter. MBY, about here, 1.641 is parallel, so no moment. Only 1.1094 has moment, but its moment is opposing this positive direction by right thumb rule, so it is also negative. Negative 1.1094 times 0.1 moment arm. So negative 1.1094 times 0.1 is negative 0.1109 kilonewton meter. Then MBZ, this is the positive direction. 1.1094 passes through Z, so it's 0. 1.6641 is opposite again in that direction, so negative 1.6641 times this distance, which is 0.2. So MBZ is negative 1.6641 times 0.2. So it is equal to negative 0.3328 kilonewton meter. So in vector form, MB is negative 0.1664I, negative 0.1109 J, negative 0.3328 K kilonewton meter. Then in vector form, MB is R BD cross F or RBC cross F. So MB is RBD cross F. You can also have RBC cross F. I will leave RBC cross F to you as your additional exercise. I'll just present RBD cross F. The position vector BD is negative 0.2I and positive 0.1 K, 0 along Y. So negative 0.2I, then positive 0.1 K. So negative 0.2 I, 0 along J, then 0.1 positive along Z. Then components of force, unit vectors, copy the first two column elements, then expand. So 0 along I. So along I we have minus 1.6641 times 0.1, which is equal to that. Along J, negative 0.1 times negative 1.1094 minus 0, so negative, so it is 0.1 times negative 1.1094, which is the same as that. Then along K, negative 0.2 times 1.6641 minus 0, so it's negative 0.2 times 1.641, which is the same as this. Therefore, MB is the same quantity, negative 0.1664I minus 0.1109J minus 0.3328K kilonewton meter. So the other one, as I said, is MB is RBC cross F, but I will leave that to you. So for your part, this is your problem. Traffic light is steadied by cable AB. If the tension in this cable is 4 kilonewtons, determine the moment about point D of the force this cable exerts on the pole. The moment of this force about the base C. So I want you to solve this into two ways, scalar and vector approach. Now for the vector approach, you might be able to present two ways, so present also in two ways and show that these are the answers. So this is your part. I hope that you can verify these answers so that for other problems you are convenient enough to solve moment of a force about a point both by the scalar and the vector approach.